We have been learning about the moment of a force or many forces. What we have learned so far is that the torque about origin O, so that I will indicate by this, is R I cross F I, where we are applying these different forces F 1, F 2, F 3 and so on about point O. We have also learnt that the torque is origin dependent. There is a very special case when the total force on the body is 0, then torque is independent of the origin, no matter about which point it is taken, it comes out to be independent. Then as a very special case of this, we define a couple moment which is nothing but two equal and opposite forces separated by a distance d. In this lecture, we study moment a little more. We will define the moment of a force or a torque about an axis. Then I will give you an example to show you what you have been learning in 12th grade and our definition is the same. Then we go on to discuss the different elements in mechanical systems or civil engineering systems and what kind of forces do they apply with examples. So, we are going to study in this case the moment of a force about an axis. Why this is important is, a lot of times, for example, you have situations where something is actually made to rotate about an axis, this axis of a rotating disc I may have fixed in ball bearings which are fixed in some place. In that case, no matter what force you apply on the disc, the only component that is responsible for its rotation is that in the plane of the disc. And then if you recall your 12th grade physics, you have been defining torque about an axis as force times the perpendicular distance of the line of force from the axis. Now, we will get more sophisticated now that we have mastered the vector algebra and so on, and define the torque about an axis in a slightly different manner, which I will show through an example is equivalent to what you have been learning. So, let us say there is a disc which is rotating about a fixed axis which is in the direction of unit vector n, and there are various forces working on it. Then the torque about the axis n is going to be equal to the dot product of n with respect to the total torque about, say, the origin O. Although I am writing origin O, the torque about an axis is actually independent of where this origin is taken, because it only depends on the perpendicular distance of the forces from the axis. So, this I can write as n dot summation I R I O cross F I, and to emphasize that this is really independent of the origin, I will write it further as n dot summation I R I. I have removed this index O cross F I. This is the component of the total torque along the direction of the axis, and this is what I will call the torque about axis, let us say n. If you really work it out, what is happening is, since the axis is fixed, it is held by certain forces. No matter what forces you apply on the disk, the forces generated at the point where the axis is being held are such that they will cancel certain the applied forces and certain components of them, and then only force that is responsible for the rotation of the disk about this given axis is that which is in a plane perpendicular to this axis, and more effective it is if it is farther away from the axis. This you know from intuition and from your whatever you learned in your 12th grade. In a similar manner, the couple moment about an axis is the couple moment tau dot n, tau about an axis. Exactly the same thing as a torque, because couple moment is nothing but a very special torque. Let us now see if this sits well with our definition of torque about an axis is equal to force in the plane perpendicular to the axis times the perpendicular distance of the force line from the axis. This is the definition you have learned in your 12th grade. So, as a simple example, let me take a disk which is free to rotate about the z axis. Let us say this is the x axis, this is the y axis, and z axis is coming out of the plane. Let the radius of this be 30 centimeters, and let me apply a force at point r is equal to 10 I plus 10 j. In xy notation, it is a point 10 10, a force which is, let us say, 30 I plus 20 j minus 10 k. So, I am applying a force at this point which is like this in the plane of x y, and it has a z component also minus 10 k. So, therefore, going into the plane of this board. The torque, total torque due to this force is going to be equal to r cross f. Again, I emphasize, recall from your previous lecture, that this r could be anywhere along the line of action of this force. Right now, we will take r to be 10 I plus 10 j. So, this is equal to 10 I plus 10 j cross 30 I plus 20 j minus 10 k. Let us work it out, and it comes out to be 200 I cross j, which is k. I cross k is minus j. So, minus minus plus 100 j, j cross I is minus k. So, minus 300 k, and j cross j is 0, j cross k is I. So, minus 100 I. So, this comes out to be minus 100 I plus 100 j minus 100 k. That is the total torque, but I want to find the torque about axis z, because this disk is free to rotate about axis z. So, that torque, so let me make the picture again. Here is the disk. The torque came out to be minus 100, let us see, this is minus or plus, minus 100 I plus 100 j minus 100 k, torque vector. So, torque about z is going to be k dot the torque, and which is going to be minus 100 Newton meters. Minus sign means that this is pointing in the direction of opposite to z. Therefore, the disk would tend to rotate with the right hand rule in the clockwise direction. This is the sense of rotation of the disk due to this torque. So, torque about z is coming out to be minus 100 Newton meters. Let us see if this is consistent with what we have been learning in our 12th grade. So, the line of force along which the force is working is this. The force is 30 I plus 20 J minus 10 K. As I said earlier, the only component of force that is responsible for rotation about the z axis is that in the plane perpendicular to the axis. So, only these two components. So, it is only these two components or the force in the plane of x and y that is going to be responsible for the rotation of the disk. And therefore, first thing we do is for tau about z, we ignore this force, the component of the force along the z axis. It cannot apply any force about the z axis. So, tau about z is going to be given rise to by 30 I plus 20 J. What is the magnitude of the force? It is 30 square plus 20 square. So, that comes out to be 900 plus 400, that is 10 square root of 13 newtons in this direction. I want to find the distance perpendicular to this force, that is this distance d from the origin. Let us find that. Let me make the picture again. So, as far as the rotation of the disk is concerned, a force is acting on this of the magnitude 10 square root of 13 newtons along this line, which is given by the vector 30 I plus 20 j minus 10 k. This we have ignored. So, in the plane x y, this is given by this. So, this line has a slope of 2/3 and it is passing through the point 10 10. Therefore, the equation of this line along which the force is working is y minus 10 is equal to 2/3, that is the slope, times x minus 10, and therefore, 3 y minus 30 is equal to 2x minus 20, or 3 y is equal to 2x plus 10. I want to find this distance along the line perpendicular to this force passing through the origin, and therefore, the slope of line perpendicular to the force line is going to be minus 3 over 2. Let me make the figure again. This is the disk, here is the force acting, and I am interested in this distance. The slope, the equation of this line is 3 y equals 2x plus 10. Therefore, the slope of this line m is going to be minus 3 over 2, and it is passing through the origin. Therefore, the equation of this line is going to be y equals minus 3 over 2 x. The line along which the force is working is 3 y equals 2x plus 10, and therefore, I can find out what the intersection point is. You work it out and you will find that x comes out to be equal to minus 20 over 13 and y comes out to be equal to 30 over 13. And therefore, this distance d perpendicular from the origin or the axis of rotation to the force line is going to be equal to square root of x square plus y square, which will be equal to 10 over root 13 meters. So, we have F, we have D, and therefore, the moment can be found out. The force is like this, whose magnitude is 10 square root of 13 newtons. We have found this distance, which is D is equal to 10 over 13 meters, and therefore, the torque about axis z is going to be 10 root 13 times 10 over root 13, which is 100 Newton meters, and because of the direction of force being this way, the sense is clockwise. This is exactly the same as we found earlier, which was coming out to be minus 100 Newton meters. So, you see the two definitions are consistent. So, let me now summarize what we have learned about torques. Torque 1 is equal to Ri cross Fi summed over. 2, torque is independent of origin if summation Fi, that is the total force on the system, is 0. Third, that torque about an axis in vector direction unit vector n is n dot tau.